So this is video conferencing and the solution and how we've modelled it within Abacus by Philomtage myself. So to give a brief introduction, I'm going to demonstrate the approach for modelling for the video conferencing solution with Abacus, the features and properties that we've utilised within Abacus, and also the conclusion and benefits of using Abacus for this solution. So obtaining architectural information from the initial outset, we had to get the design documentation. We also had to liaise with the architects and also the subject matter experts. So this picture here is an extract from an architectural Word document which gives an overview of the solution. So I've gone through that and I've actually put it into Abacus now. So you can see various components within Abacus. We've got a switch, we've got servers, we've got IP network, the endpoint, and we've also got the ISDN network. Also, to add to this, for example, if you look across to the right of the description, we can look at the actual component in detail and also apply the description to it. So you've also got an added richness of information as well within this model, but that you wasn't able to achieve with the Word documentation. So the features we use within VC for Abacus, we looked at the different views, what we could do, and we also used performance analysis. So first of all, I'll go through the views. So we've got a use case view, a call distribution view, a call flow to infrastructure view, and an infrastructure view. So these views are representations, slices of a single fully connected model. Each box and line in the view represents an actual component or connection in the model. So the same component or connection in two different views has only one manifestation in the model, so there's no duplicates. So if for example, if you've got two different views and you delete one connection from that view or a component, it will be replicated in the other views in which that manifestation occurs. So you don't get any duplicates and it's always consistent throughout the model. So this is the first view then. We've got a use case view. So basically we've got a DWP person and they're interacting with the video conferencing system. So we can see they can do booked multi-point VC calls, ad hoc point-to-point VC calls, and booked point-to-point VC calls. So this then maps down onto our call flow distribution. So we've got calls there and we've got these different coloured lines indicate the different frequency of the occurrence of the call. So we can see that the red and the green and the olive colours indicate that. So the SD point-to-point call, the booked multi-point call, and the HD point-to-point. So these have got steps, and then these map down onto the infrastructure. So this is how we map a call flow to the infrastructure. We have various endpoints at the top, and they interact with the call flow steps. The boxes within the steps here are the actions, and these actions implemented by certain components within the infrastructure. So we can see here these actions hit this capability. This is a logical capability which then incorporates the properties of the physical architecture infrastructure underneath. So now we're looking at the actual infrastructure without the call flow mapping. It's the same sort of view, and we can see the connectivity between the different components. And also, if you take a look to the right, you can look at the type of component that we've selected. So we're looking at a server, and it has implementations for that particular component, and we can set the properties down in the bottom right of what actually can occur within this server. So look at the simulations now. So the simulations we've used in video conferencing are just the performance one, but there are other ones available. So we've got reliability, availability, and total cost of ownership. So we'll just look at the performance simulation. So we've got an as is, which is just the architecture as it is today, which has been baselined and been verified by the architects themselves. And we've also got a 2B, so that's where we would like to be, or what perceived load can be added to the system. So first we'll look at the as is. So here we have the as is performance simulation. I've run the performance simulation, so now if you look down here on the right hand side, we can see that the message rates the processors and the speed, and also the utilisation. So at this message rate with 135 processors, we've got a utilisation of 47%. So this endpoint is roughly running at 50% capacity. So to just take it forward, we thought, well, if we increase the capacity of this model by, you know, the load on the system by 60%, where would it actually take us now? So this is where we perceive that we want it to be. So if we increase this load by 60%, we can now see that the message rate down the bottom right has gone up. The processors still remain the same because we've not increased any endpoints, and also we can look at the utilisation now, which is 72%. So we've actually increased that, but we're still within the boundaries of our system, albeit that we're processing slightly higher than we were before. So we want to compare these two architectures, because just looking at the figures within the properties is not an efficient way of analysing the model. So we can have a look at creating graphs. So for example, here we have a comparison of the capability. So we can look at the various capabilities of the model and the properties that we've set. So the red dotted line within the actual comparison model here is the original as-is video conferencing model. So now we're looking at when we've applied our 60% increase to the load on the system, we can see the yellow line has appeared, and we can see that we've got increases in almost every aspect apart from response time. So we can look at the utilisation rate, for example. We know that that's increased, that's gone up, but it's still within its maximum capability. The throughput has obviously increased, and that's still in its maximum capability. So there is scope here to increase the throughput more before we actually end up with our system becoming too overloaded. So conclusion and benefits then, we've got improved clarity of solutions. We've also got all the solution documented in one place. And we've got an improved understanding of the structure and connectivity now, so we can see the code flows and how they map onto the actual infrastructure. We can see what part of the infrastructure is being impacted at any one time, and also we've got accurate performance metrics now which we've obtained. So we can then work on theoretical architecture evolutions and test these scenarios. So for example, as I showed earlier, we increased the throughput of the system by 60%, and so the utilisation increased. So we can then create more focused testing areas in which to look at within the model. So from this we've got exportable data now which we can have in XML or Excel, and we can interchange this between different platforms or modelling software. So we are recognised now by the DWP as having a structured way of documenting the architectural solution. For example, we've adopted a pan organisation and business notation, so we're using like Archimate and UML, etc. So we can interface with the DWP at a much higher level, but still obtain our structural integrity down at the lower level, and use the notation that we see fit for that. So if you've got any more questions, just send me an email. It's phil.free.armitage@bt.com. I'd be happy to answer any. Thank you.